The binomial theorem is a pretty useful tool in the arsenal that tells us essentially how to expand powers of some, right? In our case, a plus b to the n. And it basically helps us to find all the possible ways to combine a and b. So in our case, if we were to expand our power of some here, we'd get this series, right? And obviously since the power is arbitrary, the series is arbitrary, right? We're using n. But now another useful side effect of the binomial theorem is that we can derive some inequalities from it to help us in proofs and proving limits and Riemann sums and whatever we want to, right? How we normally see this in questions is A is 1, B is H, such that we have some form of 1 minus H to the n, right? Which is basically saying, um, you know, most of something. So we're trying to prove most of something, or 1 minus a small fraction. Or really this is just 1 minus h, where h could be like an error term, or probability of failure, or even step size. So you'll often see this sort of form of the binomial theorem used a lot. And so having some inequalities under your belt and theory behind those inequalities will really help you. So actually applying the theorem now to our form of 1 minus h here, if we look at the series, it tells us that, well, it's n choose k times both of the factors to a different power. So in our case, n obviously remains the same because it's our power. K starts from 0. N choose k times, since a is 1, then it's 1 to the n minus k times b to the k, so h to the k, right? And 1 will, no matter what exponent, will always be 1. So we can almost just ignore that. And so this becomes the series of n choose k to the hk, or to the h to the power of k. And if we start to evaluate this for each of the factors as if we were expanding this power sum, well, for k0 we get our n choose 0 times h to the 0 plus our next term, so n choose 1 times h to the 1 plus n choose 2 times h to the 2. And you can sort of see where this is going, and it goes on forever until our n choose k, or n choose n really, times h to the k. H to the n. So this essentially becomes, if we recall the sort of formula behind this, well, it's n factorial to the 0 factorial times n minus 0 factorial times h to the 0, which just becomes 1. Plus n factorial over 1 factorial n minus 1 factorial times h, and then our n factorial times 2 factorial, or over 2 factorial times n minus 2 factorial times h squared plus all the way to, if we were to develop this, right, our last term essentially, which we can simplify this to be n factorial on n factorial times 1, which just becomes 1, and this will be n factorial on n minus 1 factorial, which, if you think intuitively what factorials mean, this will just cancel out to be n times h, plus n factorial over that, which would be n times, because if you develop each of the factorials again, it would cancel out all the terms after n minus 1. So we're just left with n minus 1 over our 2 factorial, so 2 times h squared plus everything else. And so intuitively, since this series goes on forever, or not forever, hypothetically forever, arbitrarily forever, then if we were to cut out all of what is over here, well, obviously, just this part is below the entire series. That is an inequality. It's a bound, correct? Such that we made our first discovery. That this whole expression is below our first 3 terms. Since we cut out all the rest, it's smaller. Or sorry, smaller. So 1 plus n times k plus n minus 1 over 2 times h squared. Now, using that same logic of knowing something is smaller by taking out factors of the sum, right? Parts of the sum. Well, you could also say that this is below, or that this power sum is above, say this, our first 2 terms, 1 plus nh. And you could say it's also above this part. So n times n minus 1 divided by 2 times h squared. So I just thought those would be a cool little inequality trick to help you in your questions.